Imagine a time when we believed our Milky Way galaxy was the entire universe. That was the prevailing view at the start of the 20th century. But one man, Edwin Hubble, was about to shatter this illusion. Working at the Mount Wilson Observatory, Hubble embarked on a journey that would forever change our place in the cosmos. Hubble focused his keen eye on what were then called spiral nebulae. Were they gas clouds within our own Milky Way? Or were they distant island universes, entire galaxies just like our own? Hubble used a special kind of star, a Cepheid variable. By comparing their true brightness to how bright they appeared from Earth, Hubble could calculate their distance. In 1923 and 1924, Hubble found Cepheid variables in the Andromeda Nebula. His calculations were stunning. Andromeda wasn't a nearby cloud, it was another galaxy. Suddenly the universe wasn't just our galaxy, it was a vast ocean of galaxies. This discovery moved us from the center of everything to a tiny speck in a cosmic ocean. Hubble continued to measure the distances to more galaxies and noticed something peculiar. Their light was red-shifted. A redshift meant these galaxies were moving away from us. This relationship became known as Hubble's law, the cornerstone of modern cosmology. The universe wasn't static, it was expanding. Edwin Hubble's discovery of an expanding universe was revolutionary. For decades, astronomers worked to refine our understanding of this expansion. They sought to measure its rate, the Hubble constant, more precisely. Earth's atmosphere blurs our view, limiting the precision of ground-based telescopes. We needed a clearer window to the cosmos, a sentinel in space. That dream became a reality with the Hubble Space Telescope. Launched in 1990, the Hubble Space Telescope, or HST, soared above the distorting effects of our atmosphere. Despite an early optical flaw, HST began to deliver breathtaking images and groundbreaking data. One of its key missions was to observe Cepheid variables in even more distant galaxies, refining the Hubble constant. Then came a discovery that no one expected, a true cosmic curveball. In the late 1990s, two independent teams of astronomers were using HST and ground-based telescopes to study distant Type Ia supernovae. Instead of finding that the expansion was slowing down, they found the opposite. The expansion of the universe is accelerating. Scientists named this mysterious force dark energy. Dark energy became a central pillar of the standard cosmological model, lambda CDM, but its true nature remains one of the biggest mysteries in science. The Hubble Space Telescope gave us an incredible view of the universe, but even Hubble has its limits. Enter the James Webb Space Telescope, or JWST. Launched on Christmas Day 2021, JWST is an engineering marvel. With its massive gold-coated mirror and advanced infrared instruments, JWST is like a time machine. Its primary mission is to peer back to the cosmic dawn, witnessing the birth of the first stars and galaxies. Almost immediately, JWST started delivering astonishing results. It began spotting galaxies that appeared much earlier than predicted. These findings sent ripples of excitement through the astronomical community. Stellar paradoxes M92 and the Methuselah Star. Long before JWST began its work, astronomers were already grappling with objects that seemed to challenge the accepted age of the universe. One such enigma is the globular cluster M92. Globular clusters are ancient, densely packed collections of hundreds of thousands, sometimes millions of stars. M92, located in the constellation Hercules, is one of the oldest known globular clusters in our Milky Way. Astronomers estimate the age of stars in these clusters by studying their stellar populations. For M92, various studies have yielded age estimates that are very old, often clustering around 13 billion years or even more. Given that the universe itself is estimated to be 13.8 billion years old, this means M92 formed very early in cosmic history. Then there's the case of an individual star, HD 140283, nicknamed the Methuselah Star. This subgiant star is relatively nearby, in cosmic terms, and its properties can be studied in great detail. Early estimates of Methuselah's age were truly shocking, some suggesting it could be as old as 16 billion years. More recent analyses have revised Methuselah's age downwards. The current best estimate is around 14.27 billion years, with an uncertainty of about 0.8 billion years. This means its age is now statistically consistent with the age of the universe. These stellar paradoxes serve as crucial testbeds for our understanding of both stellar evolution and cosmology. Rethinking time. The 26.7 billion-year universe hypothesis. The James Webb Space Telescope's discovery of mature galaxies in the early universe has sparked debate about cosmic timelines. If galaxies formed faster than our models predict, are our models incomplete? A radical idea suggests the universe might be 26.7 billion years old. Physicist Rajendra Gupta proposes this to address the early galaxy problem. If true, these galaxies would have had more time to develop. The hypothesis involves tired light and evolving coupling constants. Tired light suggests photons lose energy over cosmic distances. This could affect redshift interpretation. This hypothesis challenges the lambda CDM model, which is widely supported. The 26.7 billion-year hypothesis is intriguing but not mainstream. The Hubble tension, a crisis in cosmology? Beyond the puzzles of ancient stars and early galaxies, there's another simmering issue in cosmology known as the Hubble tension. This isn't about whether the universe is expanding, that's well established. Instead, it's a disagreement about how fast it's expanding today. The expansion rate is quantified by the Hubble constant, h-dallo. Measuring h-yo accurately is crucial for determining the universe's age and scale. The problem is that different methods of measuring h-yo are yielding persistently different results. One set of measurements comes from observations of the early universe. Scientists use the cosmic microwave background, CMB, as measured by the Planck satellite. This method consistently gives a value around 67 or 68 kilometers per second per megaparsec. However, measurements made using late universe methods give a different answer. These methods typically involve building a cosmic distance ladder. Prominent teams such as SH0ES consistently find a higher value for h0, around 73 or 74 kilometers per second per megaparsec. The error bars on these two types of measurements have shrunk over the years, but the discrepancy remains. This Hubble tension is a major headache for cosmologists. Resolving the Hubble tension is a top priority in cosmology, as it could unlock new physics and lead to a more complete understanding of the universe's evolution and ultimate fate. Cosmic conundrums and future visions, multiverses, cycles, and JWST's quest. The puzzles we've encountered stretch the boundaries of our cosmological understanding. One idea is the multiverse hypothesis. Our universe might be one bubble in a vast cosmic foam. Another idea is a cyclic universe with expansions and contractions. The James Webb Space Telescope provides crucial data to test our theories. Understanding the universe is one of humanity's oldest endeavors.